Today we are going to discuss what is a three-phase system. Okay, so we have up to now we were discussing about single-phase systems, but from now on we are going to discuss what is a three-phase system, how a three-phase voltages are generated. Okay, what are the relationships between the line voltage and the phase voltage, how line currents and phase currents are related, etc., etc. Let's get into the details. Three-phase systems. Three-phase systems are widely used for generation, transmission, and distribution and utilization of electrical energy because of some inherent advantages. Let us first see what are the advantages. Okay, so the main advantages of three-phase systems are as follows. One, a three-phase machine has a smaller size. A three-phase machine has a smaller size, than a single phase machine of the same power output Okay, two, the conductor material required to transmit a given power to transmit a given power at a given voltage over a given distance by a three-phase system is lesser than that of an equivalent single phase system. Okay, so to transmit a given amount of power over a given distance at a given voltage, okay, to transmit power over a given distance, then a three-phase system needs lower amount of conductor material, okay, than a single phase system. Three-phase motors are simpler in construction. Three-phase motors are simpler in construction smaller in size, that we are already seeing. They start more conveniently, run more smoothly, and are more efficient than equivalent single phase motors. So because of these inherent advantages over single phase systems, we commonly use three phase systems. Okay, so how we can generate a balanced three phase supply? Next topic, generation of a balanced three phase supply. Okay, how to generate a voltage? On the basis of Faraday's law. What is Faraday's law? Whenever a time-changing magnetic flux links a coil, an EMF is induced. Okay, so we know how single phase voltage is being generated. Here you have a north pole, here you have a south pole, there's a coil which can rotate in between. Okay, So as the coil rotates, what happens? It will cut the magnetic flux and hence an EMF is induced. Okay, so this was the case of one coil. Okay, phase essentially means coil or winding. Coil or wind. Okay, so this is the case of single phase EMF generation. We had only one coil. Okay, keep in mind when I drew a coil like this, it is simple, but understand that within a single coil itself there will be multiple turns. Okay, there will be multiple turns may be there. Okay, multi-turn coil. Right. Anyway, that is not the topic for the present discussion. So to generate an EMF, you need a coil. So in a three-phase power generation, you must have three coils which are kept 120-degree apart with respect to each other. Okay, so that's what I'm going to draw here. Okay, so here this is the magnets. Okay, so what I'm drawing here is what is called a rotor, right? A rotor. It's a cylindrical rotor. Okay, excuse me for my drawing inaccuracies. Okay, it's a cylindrical rotor, right? So in this rotor, you will place conductors. Okay, so there will be, see, so you see, let me mark this as this coil as say this is the forward path A, this is the return path A dash. Okay, so similar to A dash, there will be three coils A dash, B dash, and C dash. Okay, so these three together will constitute a three phase. Okay, so let me mark this first here. Okay, so here I have conductor A. Okay, A, this is the return path A dash. This is the return path A dash. Okay, return path A dash. Okay, so it will be wound throughout. Okay, so this is the rotor, right? Rotor is a cylinder kind of thing. We are just seeing, taking the cross-sectional view. Okay, so if this is A, it will be wound across the rotor, right? A dash. Okay, like that. So it will be something like this. A dash. Okay, now 120-degree apart from A dash, 120-degree apart from A, we have the next coil B dash. Okay, so let me mark this as B dash. So this is B, this will be B dash. Okay, so this is B dash, and again another 120-degree from B, we have C dash. Okay, so this is C dash. Okay, so we have taken a cross-sectional view. That is why you cannot see it in this form. Okay, we are seeing just a cross-sectional view. Okay, so A dash, B dash, and C dash. Fine. Now what happens? All these things will start rotating in this magnetic field. Okay, so here we have magnetic field, and the flux lines are here. Okay, all the three coils will be simultaneously moving in this magnetic field. So you see it is rotating. Rotation can happen in two ways. One is anti-clockwise, one is clockwise. So let us assume for the time being that all the coils are moving in anti-clockwise direction, like this. Okay, anti-clockwise direction. Right? So let me redraw this thing here. Right? So instead of showing schematic, let me mark this as phase A. A dash by name I have written here. So A dash is joined with B dash to have coil B, and similarly C dash is connected also with this junction coil. Okay, so the meeting point, suppose the coils are in star configuration, suppose they are connected like this, so this point is called N. Okay, this is A, this is B, and this is C, right? So they are rotating in anti-clockwise direction, assume, right? Let X be the reference point. Okay, so if all the three are moving simultaneously in anti-clockwise direction, which winding will reach point X first? First coil A will come. After 120-degree, coil B will come. Again, after another 120-degree, coil C will come, and that rotates, and that keeps on ABC, and so on. Okay, so this is called ABC phase sequence. ABC phase sequence. Okay, so keep in mind, phase sequence means the order in which the EMF becomes maximum in the respective coil. Okay, so first EMF in A will become maximum, then followed by 120-degree. After 120-degree, coil B EMF will be maximum. And then after another 120-degree, the EMF in coil C will be a maximum. That is what is shown here. Okay, that is what is shown here, right? So first EMF in coil A becomes maximum, then the EMF in coil B becomes maximum, followed by coil C. So this is called phase sequence ABC. Okay, ABC phase sequence, right? So don't think that it starts, EMF in coil B starts from 120. No, it is there. It is continuously rotating. Okay, that is why it is extrapolated to the backward side like this. Okay, similarly, EMF in coil C will be like this. Okay, so it's continuous waveforms. Okay, so we have, this is how three-phase EMFs are being generated. Okay, so let me write something here. When three identical coils, when three identical coils placed with their axis 120-degree apart, placed with their axis 120-degree apart from each other, are rotated in a uniform magnetic field, a sinusoidal voltage is generated across each coil. A sinusoidal voltage is generated across each coil. Okay, so in all the in all the coils, sinusoidal voltage will be generated. Okay, so this is what I said. Coil A dash, B dash, and C dash. Okay, so they are symmetrically located on the rotor. Okay, at 100-degree apart. Right. Three sets of coils. A dash, B dash, and C dash are symmetrically mounted on a rotor such that their axes are 120-degree apart, such that their axes are 120-degree apart from each other. Okay, see what is this angle between A and B? Angle is 120-degree. Between B and C, angle is 120-degree, and between C and A, the net angle is 120-degree. So all the three coils are placed on the rotor 120-degree apart from each other. Okay, that is what I have written here. Okay, now when the rotor is rotated, when the rotor is rotated in anti-clockwise direction, at a constant angular velocity omega, radians per second, a sinusoidal voltage is generated across each coil. A sinusoidal voltage is generated across each coil. And since the three coils rotate at the same velocity, and since the three coils rotate at the same velocity, what happens? The generated voltages will have the same frequency. The three generated voltages voltages will have the same frequency. Will have the same frequency. Okay. Also, since the coils are identical, also since the coils are identical, also since the coils are identical, the generated voltages, have the same magnitudes, have the same magnitude. Okay, so the coils are identical since they are rotating with the same speed. Okay, they all have the same frequency, and because the coils are identical, the voltages will have the same magnitude. Okay, but that's a phase difference. But there is a phase difference of there is a phase difference of 120 degree between these voltages. Okay, voltage magnitudes are equal, but there's a phase angle difference of 120 degree between these voltages. Okay, so such a system is said to be a symmetrical system. Okay, a symmetrical three-phase system. Such a system is called a symmetrical three-phase system. A balanced symmetrical three-phase system. Balanced symmetrical three-phase system. Okay, so now you see we have seen this. These are the EMFs generated. Okay, so what will be the voltage waveforms? I can write VA dash. What is that? Suppose V is the VM is the peak value. What will be the instantaneous value of VA dash? VM sine omega t. Okay, what will be VB dash? VM sine what? Omega t minus 120. Omega t minus 120. And what will be VCC dash? It will be VM sine omega t minus 240. Okay, so these will be the instantaneous value of the voltage generated in the coils. Okay, now, so suppose we can represent this in polar form. Okay, so these things can be represented in polar form, right? So in polar form, what will you get? You will get VA dash as VM, or say VM angle 0. VB dash will be what? VM angle minus 120, and VCC dash will be what? VM angle minus 240. That is what is shown here. Okay, so this is the phase A, right? So ABC is also called RYB. Okay, R stands for red, Y for yellow, and B for blue. Okay, so if you take a reference point here, first red phase will come, then after 120 degree yellow phase will reach the reference point, and after another 120 degree blue phase will reach this. Okay, is that fine? Okay, now it can be seen that so in this phase sequence, the A phase or the red phase will be leading the B phase by 120 degree. Similarly, B phase will be leading the blue phase by another 120 degree. Okay, like that. So continuing writing, it can be seen that VA dash leads VB dash by 120 degree, and VBB dash leads VCC dash by 120 degree. Also, the three voltages reach their positive maximum values in the order VAA dash, VBB dash, V, C, C dash. Is that clear? See, if when you consider this phasor, if you consider this phasor, right? So first R, the phase R or the phase A will come. Then after 120 degree phase B or the Y phase, yellow phase will come. Then after another 120 degree, the phase C or the blue phase will come. Okay, so that will be the order in which it will be reaching its maximum peak value. You can see, okay, A, B, C, and so on. Okay, so that is what is called phase sequence. Okay, reaches in the order V, A dash, B, B dash, C, C dash. Okay, the order in which the order in which the phase voltages reach their maximum values is called phase sequence. Okay, so when the coils are rotating in anti-clockwise direction, when the coils are rotating in anti-clockwise direction, the phase sequence is ABC or RYB. That's also called positive phase sequence. Okay, if the coils are rotated in clockwise direction, if the coils are rotated in clockwise direction, then the phase sequence is CBA or RBY or negative phase sequence. How come? For example, okay, this is A, this is B, this is C, right? Assume that it is rotating in clockwise direction now. Okay, let this be the reference point X. Which one will reach first? First A will come, then comes C, then comes B, and it keeps on like that. The cycle continues. Okay, so this is called CBA phase sequence or RBY phase sequence. It's in negative sense. Okay, that's why it's called negative phase sequence. Why? Because now the coils are rotating in clockwise direction. Okay, so that is what is called CBA phase sequence or ABC phase sequence. Okay, so we'll stop here. Thank you.